Okay, so this lesson is going to be dealing with worksheet 4, and what we're going to be doing is these are quantitative acceleration problems. So first I want to help you by first off going through the steps that you should go through when you're thinking of how to get these problems solved. So for the first one, it tells us we have a poorly tuned car that accelerates from rest to a speed of 28 meters per second in 20 seconds. So first of all, I want to label this is our velocity final, this was our velocity initial, and this is our time then. So first of all, part A wants us to make a well-labeled diagram of the situation. A lot of times when solving physics problems, it's easy, or the best way to think through a problem is to actually draw a picture of it. It doesn't have to be an elaborate, beautifully drawn picture, but just a picture that you can look at to figure out how this object works. So we have a car. All right, so again, it does not have to be a beautifully drawn car. Here's my car. My initial velocity is going to be 0, and my car is going to accelerate until its final speed is at 28 meters per second. And it does this in a time frame of 20 seconds. So there's a picture. It's well labeled diagram. I have velocity present, I have my time present, and I have a direction there as well. So that would be fine for a well-labeled diagram. For part B then, making a well-labeled graphical representation of this situation. Each one of these problems can be solved by either performing the math, so the equations that we learned the other day, or by putting them into the graph and solving them graphically. So why don't we start with making the graph? So we know our time is a total of 20 seconds. So on the bottom, first thing I'm going to do is I'm going to label the time at the bottom. Oops, and let's go by fours. Sorry. 4, 8. Okay, so I went by fours on the bottom. Twos weren't really going to work. So let's see, and this just says he starts from rest and he's speeding up to that particular speed. So that means our velocity needs to start at 0, and by the end of our 20 seconds, this car needs to have been accelerating all the way up to 28 meters per second. So now why don't we label the velocity on the side so that we can also get our speeds and to get our graph here. So that means at the end, at 20 seconds, he should be going 28 meters per second. So then all we're going to do is take straight line and we're going to draw it between those two objects. So nice straight line. That would be our well-labeled graphical representation of the situation. So, couple ways we could do this. So looking at part A, just to review, yesterday we learned about equations that we could use. So think of doing this first part as I can do it two ways. One way I can do this problem is by using the equation. So I know from the other day that my acceleration is equal to my final velocity minus my initial velocity, and I'm going to divide by time. That's one way I can look at solving this particular problem. The other way I can go about solving this problem is by looking at my graph. So by looking at the graph that we have a velocity time graph. So velocity time graphs, if we're trying to solve for acceleration, we're going to look at the slope of this particular graph. So in this case, to solve this first part and every part that deals with acceleration, you always are given multiple ways to solve the problem. So whether you plug it into the equation, like is here at the first one, or whether you look at the graph and you find the slope of this line. The slope of your velocity time graph is going to give you acceleration. And the last part then, it wants to know how far does it travel in this time frame. So for the second part, again, you have two ways to look at this. You can either use an equation, like for the first one. The only difference is our equation was going to be different. So velocity is equal to change in position over time. That could be the equation that we use for this particular example. So change in position, over time. We can also look at it graphically as well. So if we wanted to look at it graphically by finding how far something went, so on our graph, we're going to find the area. So in this case, we would shade down and we would find the area of this particular triangle. That would give me, again, how far this object has traveled. So either one of those examples would work just fine. So I want to give you sort of multiple ways to look at these problems when you're thinking about solving them. So for each part, yes, I'm making you do both parts, making a diagram and making the representation of it. But once you get to part C, you can use either one you want, if you would like the math or if you like using the graph. So each one of these problems then, start off with drawing a diagram. Start off by drawing a diagram, making a graph, and then seeing which way do I want to go about solving this particular problem. So hopefully this helps you. So just to recap, two separate ways to go about solving the problem, by equations or by the graph. So I hope this helps you. Come back and look at it anytime you need it.